Welcome to today's webinar, Thickened Flame Model Development for Ignition and H2 Application, brought to you by Convergent Science and our partners at IFPEN. Thank you for joining us today for the fifth event of the 2025 Converge webinar series. My name is Matthias Sulis and I am part of the business development team at Convergent Science. I will be your host for today's event. I'm glad I can be here with you today and hear from our partner at IFPEN about the latest development in the Thickened Flame Model in Converge. Convergent Science is a rapidly growing computational fluid dynamics software company. Our flagship product, Converge, is an industry-leading CFD solver used around the globe to simulate fluid flows in complex systems. Converge features truly autonomous meshing, which eliminates all user meshing time and helps provide fast, accurate results for our client. IFPEN is a major research and training player in the fields of energy, transport, and environment. From scientific concept within the framework of fundamental research through technical technological solution in the context of applied research, innovation is central to its activities, hinged around four strategic directions: climate, environment, and circular economy, renewable energies, sustainable mobility, responsible oil and gas. As a part of the public interest mission with which it has been tasked by the public authorities, IFPEN focuses its efforts on bringing solutions to the challenges facing society and industry in terms of energy and the climate to support the ecological transition. An integral part of IFPEN, the IFP School and its Graduate Engineering School, prepares future generations to take up these challenges. Since 2015, IFPEN have been collaborating with Convergent Science to develop the Converge CFD software and utilize this platform for collaborative research with academic industrial partners. In 2024, more than 20 PhD and postdoctoral students have conducted their research using the Converge CFD software. In the coming years, IFPEN plans to work with Convergent Science to extend the capability of Converge CFD for simulating high complex processes. Now it is time to introduce our speakers for today's event, Cédric Mehl. Cédric Mehl is a research engineer at IFPEN. His work concerns the modeling of turbulent reacting flow in industrial systems, with the focus on hydrogen combustion. Part of his activity also tackles the coupling of machine learning methods with reacting flow simulation. Previously, Cédric has obtained a degree in engineering from École Centrale Paris, France, and a specialization in energy technology obtained by performing a master at Cambridge University. He has then carried out a PhD at EM2C Laboratory, France, in the field of turbulent combustion CFD. During today's webinar, if you have questions for the speaker or the rest of the team at Convergent Science, please use the question box on the GoToWebinar toolbox. Questions submitted during the webinar will be answered at the end. Without any further delay, I will now pass the ball to Cédric. Thank you all.
Okay, so the work I will present today has been performed by engineers at IFPEN, including Olivier Collin, Karine Truffin, myself, different PhD students over the years, and also in close collaboration with people at CSI, with Shuai Shuai, Yichi, or Eric, among other persons involved. So here I will be mostly interested in this presentation on premixed combustion. So it's, as you probably know, an important topic, especially with application in the industry in systems such as IC engines, gas turbines, also industrial safety. And now there are a lot of new systems based on hydrogen, ammonia, or sustainable fuel, for instance, which need further design optimization. And due to that, there is a need to develop this new system using advanced simulation tools, both to better understand the physics and also to assist the design. So let's begin with some basics about premixed combustion, which will help me to introduce the thickened flame model. So typically we solve the physics on a given numerical mesh, such as illustrated here, with given cell size. So typically for the application we are interested in, it would be of the order of a few millimeters, 0.5 to a few millimeters, even higher for industrial safety, for instance. So usually much larger than the smallest physical scale we want to resolve. And for that, we basically use models for at least the small scales. So here I will, this presentation, I will talk about large eddy simulation. Also, there are some works, especially at CSI, for combining TFM with runs. But here, in this work we done at IFP, we mostly focused on LES. And so in LES, we solve part of the turbulence, the larger scales here in blue. And we have smaller scales here represented in orange here, which are modeled. So in addition to that, we have a flame, so in premixed combustion, which is very localized and thin. And therefore, the first issue we have is that the flame is actually not resolved on the numerical mesh. So we don't have enough points to actually solve these fronts. This causes also a second issue, which is that we do not solve numerically the interaction between the flame and the smallest turbulent scales, which, as I said, are modeled. So both of these issues need an adequate model to be solved. And so this is where the Thickened Flame model comes. So it's one approach among many others. So here I will only speak about TFM, but then there are also other methods, for example, based on PDFs, which exist. So the TFM approach is pretty simple. So if we take again our scheme with the delta X and the flame, what we do in TFM is that we will thicken artificially the flame front by a factor F. And so here, so the factor F is defined based on a resolution criterion, so which I call NRES here. So typically, so this is set by the user, and typically I can say, okay, I want 10 points in the frame front, and by imposing this 10 here, I will be sure that I have 10 points numerically in the flame front. Now, if we zoom in a little bit, what we see is that actually by thickening the flame, we are losing part of the flame surface. As you see here represented in red, what would be the real physical flame surface, and here the thickened. So this is due to the thickening. We can define what we call the subscale wrinkling factor, key delta, which is basically the ratio of these two surfaces. And what this means is that actually the thickened flame would propagate more slowly than the real flame. And so this needs to be corrected. And this is actually what is done in the TFM model. We define what is called an efficiency function, which helps at recovering the correct turbulent flame speed. So I will highlight in the next slide exactly how you do it in equations. And here, so this is a small technical aspect, but since we consider, I mean, here I consider unity Lewis number. I will come back to hydrogen a little bit later. And the efficiency is simply equal to the wrinkling factor. We don't have to correct for other effects. That would be the case for hydrogen. And so in practice, how is it implemented? Well, beginning from some known scaling laws. So here the laminar flame speed and the flame thickness can be related to the diffusion, the thermal diffusion, and the reaction rate. We can actually modify the transport equation of each species so that the thickness is multiplied by F while the propagation speed stays the same, or if I might say even is multiplied by this efficiency factor, actually, what we actually aim to do in TFM. And so in practice, by using that, you can show that to perform this operation, you can multiply the diffusion by E times F and multiply the reaction rate by E divided by F. And so here, want to insist that the reaction rate is still computed using SAGE, and we just add this multiplicative term here. So it's, let's say, and can be seen as an addition to SAGE, so that the flame front is properly resolved and the turbulent flame speed is properly retrieved. And here I show just an example of an input file that you can find. So to highlight the fact that TFM can be activated and parameterized in combust.in. So it's a section for a thickened flame model. So I won't go through all the parameters, but just to show that it's actually not that difficult to use. You might need also a table for SL0 and delta L0, such as in other models in Converge. But with this table and some setting the parameters, the TFM can be run along with the SAGE. Okay, so just to recap a little bit, so we see that TFM enables a proper resolution of the frame front while resolving the chemistry. So I insist on that. And it enables a consistent modeling of the turbulent frame speed propagation with models based on physics. Now TFM has, say, some adverse or side effects. I will highlight two of them in this presentation, which in our opinion for our application are the most important ones. The first one is an over-diffusion at ignition, which can lead to artificial quenching. And a second effect is modified response of the flame to stretch. So I will go into more details later on on these effects. So basically, there are two approaches that we have imagined to tackle these issues. One of them is, let's say, pretty pragmatic. We say, okay, thickening has some side effects, so let's reduce actually the frame thickening we need. And in Converge, there is a very handy tool to do that, which is Adaptive Mesh Refinement. And so we developed some models based on AMR and TFM that I will show. And the second solution is to try to derive specific models to correct these adverse effects. So same for this, we developed some models, in particular for the stretch, which I will highlight. So it's really these two solutions which can be derived. And as I will show, actually, both of these solutions are quite complementary. So first, I will speak about the so-called the TFM-AMR model, which uses AMR to refine the flame front and decrease the thickening. So here I need to give some insights into another TFM aspect, which I didn't mention yet, which is the TFM sensor. So again, we assume we have a numerical mesh with a thickened flame. In practice, we don't want to apply thickening outside the flame because we would modify the diffusion artificially, which is not what we want. The theory of a thickened flame model only applies when you have a flame front. And to do that, we define what we call a sensor, which I write S, which is a function equal to 1 inside the flame and 0 outside. So typically, there are different ways to implement this sensor, and actually in Converge, there are different possibilities, which I won't detail, but in case some of you are interested, we are happy to answer that. So I would say the most standard sensors are based on the reactivity, while some others could be defined geometrically using Procos variables. This will maybe two approaches. And so we define the final local thickening factors as this, so that actually thickening is only applied inside the flame. So the AMR actually comes at this stage. We simply and very naturally say that, okay, we activate adaptive mesh refinement whenever we are inside, whenever the sensor is superior to 0 or equal to 1. And so in this way, we selectively refine the flame front, and we are sure that, okay, we are really optimizing the number of cells. And okay, when we do that, actually, we show that the thickening can be decreased by a significant amount because each time we divide delta x by 2. So this is quite interesting to decrease the thickening and limit its effect. So this explains how to where to refine. Now we also need to enforce a refinement level. And so instead of having a fixed user set refinement level, we can actually define it automatically in a smart way. So this is what we have proposed, and it's actually we have implemented two options to do that. A first one is to select a target thickening factor, so F target. In this case, what is done is that the cell size is adapted automatically so that the thickening stays the same. So the logic here is that if at some part of the domain we have, let's say, a thickening factor of 10, it's not necessary that in other places we refine to have a thickening factor of 2 because the accuracy will be limited by the highest thickening factors. So this was a bit the logic to define that. Then we also have a second option, which actually it's the one we use the most at the moment and that we advise, which is based on target flame thickness. So here the flame thickness is the resolved flame thickness, so it's F times delta L0, and we impose this as a target. So it means that numerically we always solve the same thickened flame thickness. So this is very important when you have variable or pressure or variable phi. because if these variations are are high, such as in IC engines, the AMR could actually be very fine and very limit your computational time. So this option is actually much better for practical cases. Again, I want to highlight here the simplicity of using setting up TFM-AMR. So once you have set up TFM, you only have to add a variable called TFM-AMR index here in the AMR.in with embed above type. So this is standard. And in combust.in, there are several parameters to set up. So either we use f target, delta target, there are different flags, and we can define the values. So it's actually, again, quite easy to set up. So now to finish on TFM-AMR, I'll just show you an example. So it's something we have done a few years ago. It's actually now a pretty old example, but it highlights very well the interest of TFM-AMR. So it's an academic setup experimented at Cambridge University. It's premixed or stratified. You have actually two inlets with two different equivalence ratio, which are set at the same value here in the premixed case and at different values in the stratified. And what we did here is that, okay, we have embedding with a coarse mesh of 1 millimeter, and we use two different AMR refinement level in the flame with a target thickening of 5 and 2.5, meaning that the delta X is here 0.5 or 0.25 in the flame front. So you have an illustration here. So if I show you some results on the temperature, so on the left here is the mean temperature, on the right the RMS with a column for premixed case and another for stratified. We see that with TFM, globally the results are good for both cases, either a thickening of 5 or 2.5. The flame position is roughly well captured. And by refining, we actually get steeper flame fronts, which is expected because you thicken less. And globally, it's even a bit closer to experiments. So we see that we're able to improve the results using more AMR. And same, we get a little bit more RMS, which is expected because, well, we are more refined and we have more fluctuations. Same for CO here. I showed some results of CO. The conclusions are the same. We are able to better predict the peak when we decrease the mesh, the cell size with the TFM-AMR. So it's quite interesting. We're able to actually improve the pollutants, intermediate pollutants results. And well, regarding the computational cost, here we show a computational cost normalized by here the reference mesh at 1 millimeter. What we did is that we do here in static embeddings in black and TFM-AMR here in red for given flame resolutions. And what we see is that TFM-AMR leads to a decrease of the cost, of course. And this decrease is even more interesting when we want to go lower in cell size. So we have a very interesting cost here at 0.25. So, well, it leads to interesting savings. Okay, so now, so this, let's say, is for a bit the mechanics and the basic setup of TFM-AMR. Then I want to delve a bit further into the modeling of the efficiency. So here I need to, well, I give you a very standard model for the efficiency, which is a Charlotte model. And what I want to highlight here is that these efficiency models are based on quantities such as the turbulent velocity fluctuation, which is U prime delta here, and a scale delta at which the fluctuations are actually computed. So what is done typically in Charlotte, the standard Charlotte, is to compute these values locally. So for example, U prime is computed using local vorticity, and the delta is a local scale. And so this is typically what we do. And we have a beta parameter, which usually we set up to be a constant. Now let's take two situations. First one where I have a uniform mesh at cell size delta X, and a second one where I have AMR for the flame front, which is represented here by the red lines. If I look at the turbulent spectrum, we have a cutoff at, let's say, 1 delta X on the mesh at cell size delta X, and a cutoff 2 divided by delta X for the fine mesh. Now, since the Charlotte model computes the U prime and delta locally, what implicitly it says for this case is that we assume that all the turbulence is actually, I mean, we have a full cascade of the turbulence in the fine mesh. Because if we, so I don't have time to detail it here, but if you look at the Charlotte model, it makes assumption about the turbulence spectrum. And in fact, actually, if you use it directly, you assume that you have a full cascading of the turbulence on the fine mesh. Now, the problem is that, okay, here we resolve turbulence up to a scale delta x, and here potentially the cutoff is lower. But there is not necessarily the time for this small scale to develop in the flame front. And so it's not clear if we can use the local U prime and delta values for the Charlotte model. And so this is what we challenged and which led to the definition of what we have called in our paper the TFM-AMR-E for efficiency model. We actually assume that the turbulent cascade might not be complete and only partial, and we developed a correction for that. And so this correction is actually based on transport equation which will mimic this partial cascading. So to do that, we defined what we called effective scales, which I call here delta effective and U prime effective, which are not the local U prime and delta value, but which try to take into account the cascading. And so we do that. There are very simple equations where we have a relaxation. So we relax this effective value towards the local delta and a local U prime with a turbulent time. And this way, we will have, let's say, a response of the model to the local the turbulence. And okay, so the delta local, we define it as a multiple of the cell size. So it's here gamma delta x, and the U prime is the corresponding velocity fluctuation computed using assuming an inertial spectrum. And the turbulent time, we define it with a constant times the time scale, which we can build from the effective scales. So here you see we have two constants, gamma and alpha, for this model. And just to emphasize a bit the behavior of the model. So for example, if tau t is much higher than 2f, so the flame is very fast compared to turbulence. Actually, so the flame will propagate, but as the fine mesh here propagates on the coarser mesh, the turbulence does not have time to cascade, basically, because it's too fast. And on the opposite, when the turbulent time is much smaller than the flame time, the flame propagates, let's say, slowly into here the turbulence on the coarse mesh, and the turbulence has time to decay. So this is basically what the model tries to do. And finally, we've simply defined the new efficiency based on the effective scales rather than on the local scales. So I will here just highlight the behavior of this model on a simple academic case, which is actually the one we used in our paper. If you want more details, so it's a turbulent, homogeneous turbulence where we have a spherical flame kernel of isooctane which propagates. We considered two conditions: one atmospheric and one high pressure, with a given initial spectrum. And we consider here gamma equals 3 and alpha equal 1 as the AMR-E parameters. So in the paper, we do some parametric analysis if we're interested. Here, I just show you the final result with these parameters, which we identified as being good. So first, I want to show you some fields. So you have here the U prime, the local U prime on the top left, and the associated efficiency on the bottom, and the effective values on the right. So you see with the local U prime, you have a very strong decrease of U prime inside the flame front, which, as said before, is due to the fact that, okay, we assume that we have a turbulence which is more solved at the finer scales. And so we have this huge drop on the U prime. And for AMR-E, you actually see that it's well smoother. So this is kind of a filtering effect due to the transport equation we solve. And more importantly, the values are larger. And this translates into a higher efficiency, as you see here. Well, it's much lower for the local U prime. And so this we have actually seen, well, I don't show it in this presentation, but that's in engines when you use that, you get propagation which might be very weak compared to some experiments. So it's better to use this model. And just quantitatively to show you a bit what happens, I show you here some results on the high pressure engine conditions and the atmospheric. So what we did here, we compared three levels of refinement in the flame. One without AMR and two with AMR 1 and 2. So these are all the different symbols here, circles, squares, and triangles. In blue, you have the TFM-AMR-E model results, and in black, the standard TFM-AMR. What we see here, so it's especially visible on the engine conditions. As you refine, basically the heat release rate evolution, the heat release rate actually is lower. So it really means that as you refine, you get a smaller efficiency and thus heat release. And when you use the TFM-AMR-E model, the results are more consistent. So it's of course not perfect. It's still a model. We have also strong assumptions here to describe the turbulence cascading, but the behavior is better. And when we use IMR, we are still able to get heat release rates which are pretty large. And also to show this, it's TFM-AMR-E is easily set up. So in combustion, there is one parameter to modify, so the U prime model, and in hidden.in, there are the two parameters gamma and alpha that can be set up. So this is available in the latest Converge version. And to give some kind of conclusion on TFM-AMR, so I showed that by refining, we can actually reduce the thickening factors and thus reduce a little bit some adverse effect of thickening that can happen. So it will be even more obvious in the next part when I talk about ignition. But refining alone is not a solution because we have unresolved effects, and actually this partial cascading effects is really a good example. It's illusion. It's an illusion to think that we can just refine and everything will be nice. There are some costs to pay because we don't resolve everything numerically. Here the turbulence, and thus we still need submodels, even when using AMR. So this is an important message, I think. And now I will go into more details about two of these effect of thickening that I discussed, that I mentioned in the introduction. The first one being the effect of flame stretch on, the effect of thickening on the sensitivity to flame stretch. And I will show you a simple model that we derived to correct that. So here, what I will show you now is a very simple, canonical case where we have a spherical flame expanding a flame. So you have burnt gases here propagating towards fresh gases. So this is a problem that can be solved in 1D. So I'll show you here a 1D solution. We can define a radius of the flame kernel, ARBG. From this radius, we can define the stretch. So it's basically a curvature. And we can define, flame displacement speed as well from this setup. So we've done that for hydrogen in atmospheric conditions. And typically on this type of configuration, what we are interested in is the evolution of the flame speed as a function of the stretch. So this is what I show here on this plot. So this is not thickened. And the standard behavior is that we have a linear asymptote towards the small stretch values and what we call Markstein length. And we have a very standard formula, which is that the flame speed is equal to the unstretched flame speed minus this Markstein times the stretch. Now we can compute the same flame using a thickening factor. So let's do that. So we, for example, take F equal to 8. We see that actually we have a strong increase of the Markstein length, and which leads to a behavior which is really far from what is expected. In fact, it can be shown theoretically that the Markstein length is multiplied by F, and so that the slope here at close to 0 is multiplied by F. So this is what we obtain. And so the response of thickened flame to stretch is actually modified in an artificial way because it is not exactly what we expect. So at IFP, we have developed a strategy to tackle that. Very simple, actually. So what we propose is to modify the diffusive properties so that to retrieve the correct Mach-Stein length. And so formally, we have new Schmidt numbers defined as factor gamma times the Schmidt number. And this gamma is estimated from 1D spherical flame and tabulated. So it depends on the conditions, of course, and it's tabulated and optimized to retrieve the correct Mach-Stein length. So since we correct diffusion, we also modify the propagation speed, and so we need also to add a correction, which is here RC gamma, to the reaction rates to retrieve the correct value of SL0. And so in practice, so this can be obtained with a lookup table. So at the moment, this is not implemented in official Converge version, but it will be in a near future with a tool to compute the spherical flames. And okay, so if we apply the model to the example I showed you before, we see that actually we are able to better predict the Mach-Stein length. So it's not perfect here quantitatively. There are also some numerical criterion in the optimization that we do. So I could be closer, I think, by optimizing a bit what we did, but we are really a good improvement of the results, and we are quite happy with that. Now, so here what I showed you is for small stretch values. We also wanted to see if by chance, by targeting the Mach-Stein length at small stretch, if we could also capture the behavior at larger stretch values. So to do that, it is more convenient to work with strain. And so we computed the counterflow laminar flames because actually large stretch value are not easily found, computed in the spherical flames because it corresponds to very small radiuses, basically. Whereas here, by using counterflow flames, we are able to go much higher. So we did that. And so here, okay, there are a lot of curves, but I will just walk you through these plots. In black, you have the evolution for the f equal 1, so the n-second counterflow flames. So it's propagation speed as a function of a normalized stretch. So here 80 is actually strain, but since it's uncurved, it's equal to the stretch. Now, if we thicken without any model, we have the blue curve. So we see that, again, we overestimate strongly the consumption speed, which is expected, as in the spherical flames. And we applied a new model. So we tested several variations in the optimization of the gamma parameter I showed. So, well, this is a technicality I don't want to get into here. But the message is the following, is that, okay, when you have small strains, the behavior is kind of good for the models. So it corresponds to the green, purple and orange, but we are not able to get the correct values at larger strains. And so this is something we see, and also people at other teams saw, is that actually this model, it doesn't enable to get correct results at large strain. So there is no model to do that, even in the literature, and something we are still working on. And I didn't mention, but for standard fuels, so we tested it for isooctane. It works actually well for large strain. So it seems very specific to hydrogen, which, well, again shows that hydrogen is quite a complex fuel to tackle. Okay, so this was for a small presentation of the Mach-Stein TFM model for the stretch. Now I will go into a second topic, which is also very important, which concerns the ignition. And I will show you actually that thickening also requires some additional model to work well with ignition. So here you see a simple example of an ignition between two electrodes that I show here, which we computed with DNS. So it corresponds to the full black line here. And what we wanted to do is, okay, let's thicken and see what happens. So the first test we did is that actually we thicken all the way from the beginning of ignition. So that would happen really if we used the standard TFM model, we would actually have this behavior. And we see that instead of having a successful ignition, we have here a very quick extinction. And the first idea that we had is, okay, let's maybe not thicken at the beginning, and after some time, we activate the thickening. So we did that, and we obtained this curve. And we see that, okay, at the beginning it's better, but then it still extinguishes. So there is still a problem. So our take on that was that we actually need at the beginning to have no thickening, but to progressively increase it. It cannot be too abrupt. And so for this, we developed actually a new model which does exactly that, which we call the TFM-AMR-I model, as I will present. So for this model, first we also implemented the energy deposition model derived from the ICIM model used in ECFM. So this is a bit independent of TFM. It can be used with SAGE and other models also. The only thing, so it extends the IC model to situation where we transport the chemical species. So we call that ETSIM, and so it enables energy deposition. And now going into the, well, what is specific to TFM, what we do actually is at the beginning, we thicken, we don't, I mean, we thicken ideally, we don't thicken, so with F equal to 1. In practice, because it's very difficult to reach AMR levels up to F equal 1, we use a thickening which we call F min, which is, let's say, a small thickening factor value. And we use a progressive activation of the thickening. And so this is done with the transport of an additional variable. So here I have just a small plot to illustrate that in more details. So at T spark here, we have the spark. So at this stage, F equal to F min, we define actually a criteria based on some variation of ignition temperature, which we call delta T ign. I will detail it in the next slide. So as soon as we are in an ignition phase, based on this criterion, we don't thicken, or we thicken at F min. And when this criterion is, when this ignition temperature becomes lower than our threshold here, we begin the thickening, but we do it progressively in a time which is here F times the flame time. So it's the second flame time where we add also a coefficient CF. So this is a user coefficient made to adapt a little bit this relaxation time. And so here I just present you in more details here this delta T ignition, the temperature. Very simply, we define an ignition enthalpy which we transport, so H ign. So it's basically an added passive in converge, for which we add a source term due to the ignition. And so this will progressively dissipates by diffusion, basically, because after the ignition source term, well, we don't have any ignition anymore. And we can build this temperature here. To highlight it here, you have 3 ISO contours of this delta T ignition in black, red, and green with different values. And what we say is that when we are inside here, these contours, we don't thicken. So as defined by the user, for example, here we see that maybe the 100 is a bit excessive, as we are really inside here this zone, and by increasing this delta T, decreasing delta T0 to 50 or 25, we get larger areas, and yes, so that's how it works. And so finally, okay, we transport this also SI here, which corresponds to the variable enable to which enables to do this progressive thickening. So of course, we have done some academic setups to test that, and in this webinar, I will just talk about one practical case that we have done, which is a two-phase liquid-fueled gas turbines, so academic. So it was experimented at Korea. Basically, the experimentalists defined several ignition points where they ignited with a laser. we have decided to perform LES with 14 locations, 6 repetitions for each location, which is a bit small, so we don't have a proper statistical convergence, but it gives already a good idea of what we can perform. So we use our new ignition model, and also we use the Markstein corrected TFM. So I don't show it in this slide, but actually we found that it was very important to correct for the stretch, even though it is not hydrogen here, it is an ethane, but we have seen a strong effect of this using this model here. So just to show you what we obtained finally, in addition to more qualitative results, so we can get a probability ignition map. So on the left, you have the simulation, on the right, the experiments. What we see is that, well, we have some points where in the experiments, ignition probability is large, and we also predict large ignition probabilities. Other points where, for example, here, the ignition probability is low, and we also have low probability. And interestingly, there are some midpoints, I would say, where the probability is around 50, 40%, which typically are difficult to get with LES. And for some of these points, we have actually intermediate values, which is quite interesting to be able to predict that. So it means that we have repetitions where it extinguishes, other one where it ignites. And of course, well, there are some points where it works a little bit less, where we have more than 30% of errors, for example, this one or this point. And here, so it can be explained by first, we only have 6 repetition, and also we have a very simplified model for injection. And for instance, the green point here, we expect that the spray is not very well described. I mean, actually, we have quantitative results, which shows that the spray here, we are a bit off. So it can be also due to the spray. But globally, we are able to perform this simulation with very interesting CPU cost. Basically, one ignition is around 34 hours on 288 processors, so it's really actually interesting. And we can foresee doing that on complex cases, even industrially. Again, the setup, I don't go in details. It's some parameters in hidden.in, which are quite easy to set up. So to conclude here on TFM-AMR-I, so we define an energy deposition model, which actually is not only linked to TFM, but can be used in SAGE. And more importantly, we we maintain the low thickening in the first ignition phase and increase it progressively. And this enables actually to get proper behaviors. Whereas if we use the instantaneous or delayed abrupt thickening, we don't get the correct behavior. Also, one thing I didn't mention, I was a bit fast, is that this behavior is most important close to minimum ignition energy. We also saw that in cases where the ignition energy was very large, these effects are a bit less important, and the original TFM-AMR is actually not that bad. So here we have selected cases where we are actually close to MIE, so when we want to predict ignition probability, which are of interest, but it is here where this model is actually the most powerful and interesting. Okay, so well, it's actually what I've said. So the cost is we have good cost. It's entirely automated, so this is also important. There is no user intervention, but the parameters are set. It works well, and we have done several validation. You have 3 papers about that, which you can see if you are interested. So now I spoke about spark ignition. There is a second problematic, which is spontaneous or auto-ignition. This I won't repeat. In spark ignition, what we saw is that if we don't use a progressive increase of F, we don't have the correct behavior. In auto-ignition, what we see is that when you apply the thickening all along, you have an overprediction of the ignition delay. So this is easy to understand because in TFM, you will divide the reaction rate by a factor F, and so the reactivity is decreased, and therefore the ignition is overpredicted. So that's quite actually natural. And so what we need to do for spontaneous ignition is to maintain F equal 1 up to the ignition delay, and then also do the progressive thickening. So there is, as you see here, a complementarity between these two spontaneous and forced ignition models. And because of that, we developed a model which we call TFM-AMR-V2, which basically considers this both of these effects. So for auto ignition, here I will just show you the principle. So the first ingredient is to detect when we have auto ignition, and this is done by detecting some burnt gases with an indicator which is called IB. So when this IB is equal to 0, so there are no burnt gases, we only use sage, and we use sage plus TFM when this factor is equal to 1. And when it begins to be equal to 1 here, we use a progressive thickening again in a time which is F times the flame time. So we have here this, so it's pretty simple. So here delta ignition is 0 because there is no added source term. So this criterion is always satisfied. And okay, so we have this thickening only when the ignition has begun. So here I have a small example to show. So you see at the beginning here, F equal to 1, you begin to have temperature, so burnt gases, and progressively the thickening factor will increase. So it's the principle is pretty much similar to what we got before. It's only the methodology to initiate the thickening which changes. And rapidly, I just want to highlight that this strategy is fully consistent and compatible with the Spark model that I've shown before. In the end, we have only one model for both ignition scenario, and so this is also convenient. It's really automated. So again, I want to explain again here. Well, in this case, you have the Spark. Delta T ignition, I mean F equal 1 or F min, which is kept until delta T ignition it becomes smaller than the threshold, and that's it. So I think I have a small video to show. Well, maybe I can go a bit faster. So F equal 1 here at the beginning because you are in the ignition phase, and progressively we get an increase of the thickening factor. So that's what I showed earlier. Okay, so this is just a recap. So in both cases, the model goes towards an auto ignition which is predicted using Sage alone, and then an activation of the progressive thickening. With spark ignition, we have the heat energy source deposition, whereas with auto ignition, we have the auto ignition depends on injection and mixing, of course. So this is a work which is submitted at the moment to Convention and Flame. It was the work of a PhD student, Sarah Feher, which is actually currently at CSI. And well, okay, that's the work that she has done. Finally, a small academic validation about this auto-ignition case. So the situation where there is auto ignition. So it's pre-vaporized dodecan jet which ignites methane air mixture. So what is done here is that we have fully resolved LES, which is called FR LES, and it is compared to the new model with TFM. So here, just to show the results, you have so 3 variations of the case with depending on the pilot size. On the top, you have the finite, the fully resolved LES. On the bottom, the TFM, and we see that as time advances, we have a very good flame behavior. And it means that the model behaves well, and we can see that quantitatively looking at heat release or temperature. The prediction is very good, and very interestingly, the computational effort is very much decreased. I mean, it's really expensive to do the fully resolved LES, and the TFM costs almost nothing in comparison, as you show here, the number of cells on the top and the CPRs on the bottom. Okay, so that closes the ignition topic. So just as a quick summary, we saw that standard TFM fails at predicting auto ignition correctly. So be it spark or actually spontaneous ignition, especially for spark, especially close to minimum ignition energy. With this new model, so the TFM-AMR V2, we are able to include both spark and auto ignition. It has been validated on academic and also on dual fuel engines. So all of this has been done in the PhD thesis of Sarah Feher. Probably further industrial validation are needed in the future using this model. So if some of you have cases that could apply for this type of simulation, we'd be happy to test this model. So now, just to finish my presentation, I have a final topic, which I just have a few slides on it because it's really preliminary work, which concerns hydrogen and especially thermo-diffusive instabilities. So here, as you all know, lean hydrogen flames are subjected to what we call thermo-diffusive or TD effects. It implies flame wrinkling, as you show here from experimental images that have been published. So it leads to a strong increase of the flame speed. So due to this increase of surface, but also to the local reactivity, because hydrogen responds to flame stretch. And LES models at the moment do not take this into account. So basically, if you plug a standard TFM model for hydrogen cases, you will underpredict this type of cases by a large amount, actually. And the objective that we have, which is something which is still ongoing, so we have a PhD student which is currently working on that. But before that, we actually tested some very simple ideas. And in fact, we wanted to see, to assess a bit the importance of these instabilities, and thus we assume that we assume the decoupling between instabilities and turbulence, and we added constant additional efficiency in the TFM efficiency. So this is what we have done here. To see what happens, and we computed this constant term from DNS of laminar unstable flames. I show some examples here. We actually did that for 2D and 3D flames. So for 2D, I can go a bit faster maybe. So you see the typical instabilities. And what we have seen actually is that for 3D, acceleration is much faster than for 2D. And it seems that taking into account 3D effects are important. So we did that for several here conditions, and we analyzed that a bit. So I want just finally to show you an example of cases that we target in the industrial safety context. So we are quite interested in this topic. And we tried to simulate an experimental setup, which was designed at INRIS, which is also another French institute specialized in safety. So it's basically a box with hydrogen and air inside, and it's ignited. So we considered an ignition at P1 in our simulations. We have a flame which develops. It's roughly laminar in the box and becomes turbulent as it is vented out of this box. In these cases, we have a very large thickening factor of 100, and therefore we could consider that all the instabilities, all the scales of instabilities are the subgrid scale. And here I just show you some results to make my point. So we had some experimental pressure probes that I show here. We first performed the model with no modeling of the instability. So we didn't add any efficiency of instabilities. We see that we have no signal at all, meaning that the flame is not propagating fast enough. Then we tested the two values for the TD instability. One of them based on 2D DNS, the other one on 3D. And what we found is that a priori it's important to consider 3D instability effects. And by taking this constant value here, we get pressure peak, which is pretty accurate compared to experiments. And also, yes, that's maybe just an illustration also that if we don't consider the stretch corrected model here, still it gives bad results. So just a point I want to make here is that in this case, because the flame curvature is very, I mean, the flame radius is very large, so the curvature is low. The stretch is actually small, and therefore the AMR-I TFM model behaves pretty well because we are in the regime where it behaves well. But when we are more turbulent and with larger stretch, the behavior would not be good. So this is a case where actually the Markstein TFM could be used for hydrogen because of the low stretch values. Okay, so just discuss that. So this computation actually showed that we need to take into account thermo-diffusive instabilities to get accurate results. And we are currently working on developing new models. So we are testing out some models from the literature. So we begin to see that there are some strong drawbacks, and we are trying to improve them and to propose a new model. So this is really ongoing. So it's couldn't make it part of this webinar, but we have made really good progress on that as well. Okay, so here comes my final conclusion. So we have seen that TFM is actually a powerful turbulent combustion model for premixed flame because it really enables to get correct flame resolution, and we have a good control over what we do, especially regarding the turbulent flame propagation. So we can really inject advanced models based on physics and be able to control and to model. So the formalism is actually quite also quite powerful when it comes to what I showed just before with the thermo-diffusive instabilities, since it is based on the concept of flame wrinkling and reactivity, and we actually solve the reactivity. Instabilities actually can be integrated in a very in an easy way, I would say. Also, I've showed that thickening can have adverse effects regarding sensitivity to stretch and ignition. And most of our work of these past years has been to design models which improve the behavior of TFM. So one model is the TFM-AMR-I for ignition, Markstein TFM for stretch sensitivity, and also don't forget the TFM-AMR efficiency for unresolved turbulence outside the flame front. So okay, so that ends my presentation. So thank you all to listening, and I'll be happy to answer questions also along with Olivier Collin, which is also which is here as well. And so we are happy to answer any question.